Okay, so last week we were studying the fermionic systems. Although formally it just looks a minor difference between the fermions and bosons, the main difference was just a couple of signs here. It just has drastic consequences for the physical interpretation for what is going on in the system. Now, one thing was the chemical potential. In the case of the bosons, we had seen that the chemical potential had to be negative, and at lower temperatures it increases, and if it reaches zero at a finite temperature, then we have what's called the Bose-Einstein condensation. In the fermionic case, there is no such limit. There is no such constraint. The chemical potential basically can take any value. Now, one thing is so this is the large temperature limit. In the large temperature limit, basically this Z is negative. We are in the classical regime where the chemical potential is large and negative, so this factor Z, which is e to power beta mu, is very smaller than 1. Much smaller than 1, so we can basically make a Taylor expansion in Z, and if we make a Taylor expansion in Z, we recover more or less the classical results. Now, for any temperature, here we set the large T limit, but this result is basically valid for any temperature, and the chemical potential is determined by N, the total number of particles, which is written as the sum over all the occupation numbers, let's say this Fermi-Dirac distributions. And for large temperature, we can make an expansion of this function f, which is given by this integral, and we basically keep the first term, and so we basically determine what the chemical potential is. Once we determine the chemical potential in terms of, in this case, the temperature, the volume, and the number of particles, remember this lambda was the thermal wavelength, it is just h over square root of 2 pi mkt. And the next thing was to evaluate the logarithm of q, the grand partition function, which was equal to, in general, PV over kt. So knowing the value of z, again, we can make an expansion in the high temperature limit in z, and we obtain the PV over nkt. Of course, the interesting thing will be what are the deviations from the classical limit. Okay, it's a high temperature, but not that high temperature. So what would be the first correction? Well, to evaluate the first correction, basically we need to solve this equation. In this case, you see, at large temperature limit, lambda is very small, because lambda is proportional to 1 over square root of t, and as t goes to infinity, lambda goes to 0. At large temperature, where lambda is very small but not necessarily 0, we can look for the first correction to z. So what we do is we just expand this function f3 half of z, which and this has to be equal to delta, and then we look for some corrections to this expression of z. What is b1, what is b2? Well, the easiest way to solve such an equation is just order by order. You just substitute such an expansion of z in terms of delta into the above equation, and you just equate them, solve it order by order. So at the end of the day, this is what we obtain for z. So it's just, and then the next thing, once we have an expansion of z, we can just put for the pressure P expression, and we get this is the equation of state, so-called the virial equation of state. Now, you see, we had also discussed it in our last lecture. There is this plus sign, there is a positive correction. So basically, the pressure is at high temperatures, the pressure of a fermion gas is slightly higher than the pressure of an ideal gas. In the case of the bosons, the pressure at a given volume, number of particles, and temperature, the pressure of a boson gas was slightly lower. The pressure of a fermion gas is slightly higher than the ideal gas. And we could interpret this as a quantum mechanical force. I mean, we had also already studied this quantum mechanical force between fermions. It was repulsive because basically the two fermions, you cannot put them in the same state. And for bosons, it's an attractive force. Basically, they prefer to be in the same state. And then, of course, once we have the expression of z, we can basically go ahead and calculate the corrections to whatever we want. And one of the interesting properties was the specific heat. And the specific heat basically, in this case, it is lower than the specific heat of a classical ideal gas. And so what happens is this red dashed line was the classical ideal gas, We had already studied the Bose-Einstein condensate, so it was as the temperature is lowered, in the case of the Bose-Einstein bosonic gas, the specificity is slightly higher, but of course eventually it has to go to zero because of the third law of thermodynamics. So there has to be a peak, and in the case of a Bose-Einstein bosonic gas, it turned out to be this phase transition from the boson gas to a Bose-Einstein condensate. And there is this discontinuity in the derivative of the specificity. Now, the phase transitions are always characterized by some kind of a discontinuity. It can be some parameter is discontinuous, or its derivative is discontinuous. So here there is a phase transition. And in the case of the fermions, we don't have such a system. The specificity is already below the ideal gas limit, and it just decreases as the temperature is lowered, and it just goes smoothly to zero. So there is no such phase transition. Now, the other limit that we were interested in was the small t limit. Now, one interesting thing about this Fermi-Dirac distribution is at very low temperature, it's almost a step function. So there should be a plot. You see, this black curve is what happens at exactly t equal to zero. As we increase the temperature, now this is what we defined as the Fermi energy. You start from filling the ground state. You see, these are fermions, so you cannot put all of them in the ground state. In the case of the bosons, we could put all of them in the ground state, so there wasn't such a Fermi energy, Fermi level. But in the case of fermions, once you fill the ground state, the next electrons you put should go to the first excited state and the second excited state, etc. So they have positive energy. And in fact, they turn out to have quite a significant kinetic energy. And their speed is a few percent the speed of light. For if you take a typical metal, the electrons in Fermi energy are moving at speeds comparable to a few percent the speed of light. And if you increase the temperature, you will be exciting these electrons, but only the electrons very close to this Fermi energy. Because if you want to, if you are at a temperature T, typically by increasing the temperature, you are giving them an energy of kT. If there is an electron in the ground state, for it to acquire this energy, it has to go to a state which has an energy kT. But since the Fermi energy is so high, it's around 10 to the power 4 Kelvin, unless you reach those temperatures, well, the ground state can only go to a state which already has electrons there, which already has fermions. So they cannot absorb this energy. Only the particles close to the Fermi energy can absorb this thermal energy and get excited to states which are above the Fermi energy. So at temperatures, even in room temperature compared to the typical Fermi energies is negligible. It's very small. Even at room temperature, you cannot really excite the electrons. They are kind of frozen. So we can make an approximation around this step-like behavior. Quite often we have such integrals of some functions multiplied by Fermi distribution. So this function is the square root of epsilon in the case of the total number, or it is epsilon to the power 3/2 if you are interested in evaluating the total energy. And so this function, we have seen that we can approximate those integrals basically in this form. So it's the first term is just what we would have obtained if we had replaced this one, the Fermi distribution, by a step function, plus we have the corrections. Then we can look for what are the corrections to the chemical potential. Well, here we probably made a mistake. This factor is not correct. It should be pi squared over 12. So probably we missed some factors in these derivations. You can go over them and just correct them. And as we expected, the specificity does go to zero at zero temperature. So that was basically where we had left. Now, any questions? Well, the rest will be basically applying these results to various systems. So these are what we had obtained. This A epsilon is the single particle density of states, and this is the equation that we need to solve to determine the chemical potential, or the Z. And the chemical potential, the first at low temperatures, this is the first correction to the chemical potential. At high temperatures, Z is just lambda cubed over GV. This is the high temperature result. Do you understand what is the epsilon Fermi? Now let's look at the magnetic properties. If you consider the electrons, okay, they are fermions, they are spin 1/2, they are moving around, but since they have a definite spin, they have a magnetic moment. So let's look at their magnet. They have a charge and a magnetic moment. So both of them, since they are moving around, they will contribute to the magnetization. They can create a magnetic dipole moment. Plus, they already have a spin. They have an intrinsic magnetic dipole moment, so they can contribute through that intrinsic magnetic dipole moment to the magnetization. So the Hamiltonian of the system will be just the kinetic term for the single particle Hamiltonian minus whatever the magnetic dipole moment is, that B. This is the single particle Hamiltonian if we have just these electrons inside the magnetic field. So basically we can just divide our electrons in two parts. Electrons with spin in the direction of B, and N minus are the electrons with spin in the opposite direction of B. So these electrons, even if they have the same kinetic energy, they will have different total energies. So epsilon 4, if they are pointing in the same direction, their energy is p squared over 2m minus mu b. And epsilon minus, this is p squared over 2m plus mu b. So let's just imagine, let's look at zero temperature. So we first start adding the electrons or the Fermi electrons to our system. So they will first fill the ground state. The ground state will have zero kinetic energy, but you see the ground state has a spin in the direction of B. So you first start adding electrons with their spin in the direction of B. Then you add the second electron. Well, unless B is very small, it will still be in the direction of B. So until the energy that you are filling acquires the level mu B, all the electrons that you add will have spin in the direction of B. Then if you keep adding electrons, only after that you start filling this, adding electrons in the direction opposite of B. So you see the reason is this one, the spin parallel to B. These states can have energy starting from minus mu B to infinity. Spin anti-parallel to to B, these states start have energies mu B, and then go up to infinity. So basically, you first have to fill, since at t equal to 0, the system is in the ground state. Well, at t, the system will be always in ground state. But if you add the electrons one by one to be in the ground state, you have to fill these states first. But that basically means that you have a net spin. The electrons have a net spin and hence a net magnetic moment. This is what's called the magnetization of the system. Now we will be interested in two properties. What is the magnetization of the system? And what is the magnetic susceptibility? Now this is basically the derivative of magnetization with B. In particular, we will be interested in the so-called divided by V also. In general, we will be interested in the small b approximation for small magnetic fields. Now, first, let's look at zero temperature, since it's clearer to understand what's going on. Then we can look for the corrections at small but finite temperature, at infinite temperature, etc. So the magnetization of the system. The total magnetization will be just mu star n plus minus n minus. This is the total magnetization of the system. N plus will be just the integral, or the sum of 1 over all single particle states of course spin up in the direction of B up to the Fermi level. So we will be the states will be filled up to the Fermi level. So the first question is, how many up states are there up to the Fermi level? Well, we can just replace this by the summation by an integration over the momentum and the volume. H cube up to, let's say, PF plus the momentum of the spin-off particles at the Fermi level. This is 4 pi V over H cube PF plus squared, no, P squared dP from 0 to PF plus n plus is equal to 4 pi V over H cube PF plus cubed over 3. This is n plus. And similarly, if you do the same trick for n minus, this is 4 pi V over 3H cube PF minus q. Now, what are these PF pluses and PF minuses? Is at the Fermi level, an electron with spin up has energy PF plus squared over 2m minus mu star b. So PF plus is square root of 2m epsilon Fermi energy plus mu star b. And PF minus would be square root of 2m epsilon Fermi minus mu star b. So we have less number of n minus states because PF minus is small. Well, that's what we were expecting anyway. So n plus, the magnetization of the system then just turns out to be mu star n plus minus n minus mu star 4 pi v over 3h cubed times 2m to the power 3 halves epsilon f plus mu star b to the power 3 halves minus epsilon f plus minus mu star b to the power 3 halves. This is our magnetization at 0 temperature. And, well, we can take the small b limit. So let's define this chi 0 to be, well, 1 over v dm by dv which is the same thing as limit as b goes to 0 m over bv, because m is 0 at v equal to 0 anyway. So this is nothing but the definition of the derivative. And this would be, we have this overall constant Well, if you just make a Taylor expansion of this around well, let's just factor out this epsilon f, epsilon Fermi to the power 3 halves from each one of these terms. So we get twice, 2 times 3 halves mu star b over epsilon f. And 0 temperature magnetic susceptibility is mu star 4 pi v over 3h cubed 2m to the power 3 halves epsilon Fermi to the power 3 halves times 3 mu star b over epsilon Fermi. No, sorry, this we divide by dv anyway. V is cancelled, this b is cancelled. So epsilon star to the power 1 half times 3 mu star. Okay, times this 3 also cancel this 3 over there. So this is what we have for the magnetization. Now the expression for the Fermi energy. Well, this is the Fermi energy of the system. We can just replace some of these factors over there. So you see, now there's no V. Now 4 pi, well, let's just take the 4 pi over h cubed. This is equal to 2m epsilon Fermi to the power 3 halves divided by 3 n g. This is the Fermi energy of the system in the absence of the magnetic field. So the zero field magnetic, the zero temperature magnetic susceptibility is mu star 2m epsilon Fermi to the power 3 halves divided by 3 n g epsilon Fermi to the power 1 half. Did I do some mistake somewhere? Yes, this is, sorry, all of this inverse. So here I have h cubed over 4 pi, I move it to the other side, So I need to move the epsilon Fermi to this side. So the zero field magnetic susceptibility mu star 2m to the power 3 halves epsilon Fermi to the power 1 half 3n over 2m epsilon Fermi to the power 3 halves 1 over g. Now these two m's will cancel. We have a somewhat simpler expression, just taking g is equal to 2. Mu star 3 times mu star n, 3 over 2, n over epsilon Fermi. This is the zero temperature result. Now, if you remember what we had done in classical electrons. In the classical case, let's just remember. Well, Q, we had defined the n particle partition function as Q1 to the n over n factorial. If we only take, or if we only assume, since we are in the classical case, we didn't look at the motion of the electrons, just the spin. Here we are also, in fact, looking at the spins. So assume just we have spins fixed at certain positions, and Q1 was just e to the power beta epsilon plus e to the power minus beta epsilon, epsilon being mu times b. Now what we had was at zero temperature, all the electrons were aligned in the same direction. So that's what we call the saturation. So T goes to 0, the magnetization was basically, since all of them were aligned in the same direction, we have n times mu star. This is the total magnetic field of this total magnetic dipole moment. Magnetization is the magnetic dipole moment per volume divided by V. So the magnetization, so magnetization had this saturation, but which basically means that the magnetic susceptibility is 0 at 0 temperature. If you change the magnetic field, nothing changes. All of them are pointing in the same direction. Anyway, but in the case of the 0 temperature, not all of them are aligned in the same direction. They cannot be in the quantum mechanical treatment. Basically, if they were to align in the same direction, that would mean they are in the same state, and we know that two fermions cannot be in the same state. That's not allowed. So this is basically what happens at the 0 temperature limit. Okay, so probably I made some mistake somewhere. Yes, here. You see, here I have a mu star. Inside I also have another mu star. So this is here I have a mu star, here I have another mu star, so this is mu star squared. Now let's look at what happens when we have a finite temperature, small but finite. And let's use the canonical part ensemble. Now in the canonical ensemble, we first need to write the En. So this is equal to sum over all P, P squared over 2m minus mu star B times np plus p squared divided by 2m plus mu star b np minus. So np plus is basically plus or minus is the number of electrons of momentum p and spin either parallel or anti-parallel to B. Plus is for parallel, minus for anti-parallel. Well, we need to write down the partition function, sum over all states of e to power minus beta E. Now the states are parameterized by the number of particles in each single particle state. So basically here we are summing over all possible sets n plus and n minus such that n plus is equal to sum of these n plus, n minus is equal to sum of the n minus, and n plus plus n minus is equal to n. So we need to sum over all such sets n plus and n minus of exponential of minus beta to m of, let's see, np plus plus np minus minus beta mu star b n plus plus n minus, no, n plus minus n minus. So basically in this term I already made the sum over p. Since this mu star b is independent of p, I can just take it out of this p summation. What remains is the sum of np plus overall p. That gives me the total number of electrons with spin in the direction of p. This is my partition function. Now let me rewrite that sum in a slightly different form. So let's say n plus can take any value from 0 to n. Then I have e to the power minus beta mu star b n plus minus n minus, and well, n minus is just n minus n plus, so I'm basically imposing one of the constraints. Since n plus plus n minus is n, I already know what n minus is, so this sum is actually 2n plus minus n. Now the remaining terms, well, I will be summing over n plus, np plus, sorry, these are the sets are over np plus values. I have a constraint in this sum. Sum over np plus should be equal to n plus. And I am summing over exponential of minus beta sum over p squared over 2m np plus. And then I have times, I need to sum over np minus with the constraint that np minus should be equal to n minus, which is n minus n plus, of exponential of minus beta sum over p squared over 2m np minus. Do you follow? You see, I have to sum over all these. The microstates are given, I specified by the sets of numbers np plus and np minus. If I have to specify how many spin-up particles have which spin, which magnetic, which momentum, and how many spin down electrons have which momentum. So that is what specifies my states. Of course, the number of electrons having spin up and the number of electrons having spin down, they have to satisfy certain constraints. Their total number is fixed because I'm in the canonical ensemble, not the grand canonical ensemble. Okay, then I can just change this sum, divide this sum into various parts. You see, n plus in principle can take any value from 0 to n. For each fixed value of n plus, n minus is also fixed. And for each fixed values of n plus and n minus, I have to sum over all sets n plus, np plus, and np minus such that they satisfy these constraints. So I'm just basically reorganizing all these terms such that first I fix n plus. For a fixed value of n plus, I sum over np, the sets np plus and np minus, multiply them, and then sum over all n plus. Now the advantage is, you see, if you look at one of these sums, let me just denote it by this one. Well, if I had imagined a system of electrons without spin, or in the absence of magnetic field, let's say, and if I wanted to calculate the partition function for this for n0 electrons, this would be what the sum that I would have evaluated. The microstates will be given by these integers np, the set of integers np, and summing over all possible sets np such that their sum is n0 would just give me the partition function. So let me just call this one Q0 of N0. I'm just giving it some name. Let me just call this one, define this as e to power minus beta A0 of N0. A0 being my free energy. As in the canonical ensemble, I just define the free energy as minus kT times the logarithm of the partition function. So going back to my expressions, now my grand partition function this time for n electrons is now, okay, there is the sum over n plus from 0 to infinity of e to power minus beta mu b 2n plus minus n. It is this term over here. Then I have this sum over np plus, well, this is nothing but this sum over here, Q0 with the number of electrons is n plus, or e to power minus beta A0 n plus. And then I have the other sum. The other sum has the same mathematical form. The only difference is instead of n plus, the sum of these integers is n minus n plus. Or Qn would be just sum over n plus from 0 to infinity, exponent of minus beta mu b 2n plus minus n plus A0 n plus A0 n minus n plus. Oh, sorry, not infinity. This is up to n. Now back to large numbers. Which one?
In the first line. What is MP in the X1?
This one.
Yes.
Well, you see, this is just a hypothetical system. This is a definition. This is a hypothetical system of spinless electrons, still fermions. And if I would have asked the question, what is their partition function of N0 electrons, spinless electrons, then this is what you would have evaluated. So Np are the number of spinless electrons having momentum p. And I'm summing over all possible sets Np such that the sum of the integers is N0. And I define this partition function to be Q0. So basically Q0, N0 is the partition function of spinless N0 electrons. Now, back to here. This is my Qn. We have seen many cases where we had these sums of enormous number of terms. N is an enormous number, 10 to the power 20, 10 to the power 30. And among these enormous number of terms, almost all the terms were 0. There was only one term which was enormously larger than the other ones. So in this sum, I can actually replace this sum by the largest term in that sum. So Qn will be approximately equal to exponential of minus beta mu b 2n plus, let me just put the bar, minus n plus a0 n plus bar plus a0 n minus n plus bar. If I evaluate this derivative at n plus is equal to n plus bar, this should be equal to 0. This is the largest term in the sum. Now let's just take the derivatives. Twice mu b plus dA 0 by dn plus minus dA0 by dn minus. Evaluate both of these derivatives are evaluated at n plus is equal to n plus bar. This should be equal to 0. So do you remember what is the derivative of the free energy with respect to the number of particles? You see, dA, our thermodynamic relation tells us that this is minus SdT minus PdV plus mu dN. So dA over dN is nothing but my chemical potential. So this condition basically gives me that this is the chemical potential mu 0 evaluated for n plus electrons minus mu 0 evaluated for n minus electrons plus 2 mu b. This should be equal to 0. So here I have a sign mistake. You see here there is a minus sign, minus beta. The coefficient of NP plus is also minus. So here the sign is plus. So this sign over here is plus. This is plus, this is minus. This is minus, this is minus. So this is my condition. Now I will be eventually looking at the low B limit. Oh, okay, sorry, before going on, this is a condition I have in equilibrium. Eventually I will be looking at the low magnetic field susceptibility. So B will go to 0 and N plus and N minus, their difference will go to 0 in the limit that I am interested in. So let me first define some number R as N plus over N. Minus 1/2. Basically because R will go to 0. In the B goes to 0 limit, so I can make an expansion in R. So this tells me that N plus is equal to N times R plus 1 over 2, and hence N minus is equal to N times R minus 1 over 2. So this condition tells me that mu 0, N plus, so mu 0 evaluated at R plus 1/2 N minus mu 0 R minus 1 over 2. Sorry, this is minus R plus 1 over 2. 1 over 2 minus R times N. This should be equal to 2 mu B. So as if B goes to 0, R also goes to 0. So that's why I will be making a Taylor expansion in R. So that will tell me that the derivative of mu 0 xn with respect to x evaluated that x is equal to 1/2 times the R minus derivative of mu 0, again x at xn at the value x is equal to 1/2, the whole thing I'm just calling x, times minus R, this should be equal to 2 mu B, or I know what R is. It's just mu times B divided by derivative of the chemical potential of xn electrons with respect to x. Of course, that derivative has to be evaluated at x is equal to 1/2. Now, of course, we are not interested in R, but we are interested in the magnetization. Magnetization is, again, just mu star N plus minus N plus minus N minus. Well, their difference is mu star N. Well, if I just subtract N minus from N plus, I just get 2R. This is my magnetization. So M, the total magnetization of the system, is just 2 mu star N. R, I had already evaluated it, mu 0, mu star, sorry, B, over the derivative of mu 0 with xn with respect to x, evaluate that x is equal to 1/2. Magnetic susceptibility is mu over Vb, m over mu b, limit as b goes to 0. This is 2 mu star squared, and the density derivative of mu 0 xn with respect to x, evaluate that x is equal to 1/2. So if you want to find the small temperature susceptibility with its correction, the only thing we need to do is just calculate this derivative at low temperatures. Now, what is the we had already studied the the chemical potential for a fermionic system, and what are the corrections to it. So if we go back to our previous result, so this is the chemical potential, and this is the Fermi energy. Now let me just clean it a bit. This is pi squared over 12. And this n is just n over v. So you see, the chemical potential is proportional to the number of particles to the 2/3. Nothing else depends on the number of particles. This is the mu for n particles. Now, mu for x times n particles is proportional to x to the power 2/3. And there's no other x dependence. This is the only x dependence. So the derivative of mu with respect to x is just 2/3 mu over x. This is what I will be using. So let's go back. This is our susceptibility. This is equal to 2 mu star squared n divided by 2/3 mu. X is 1/2 twice mu. So 3/2 mu star squared n over mu. This is for kT much less than the Fermi energy. Well, I know how mu changes with temperature. So if you like, we can just say that kT is equal to 3/2 mu star squared n over epsilon Fermi. Now 1 over mu is 1 over this number. This is a very small 1. Let's just put the plus. Instead of this minus just becomes a plus if we make an expansion. 1 plus kT over epsilon Fermi squared times pi squared over 12. Now we already recovered the zero temperature limit, and we also know the correction to it. Let's look at the large temperature limit. We should recover the classical result at the large temperature limit.
Can we have a break?
Okay. Well, there are really the two things I would like to do. This large temperature limit, which I hope will be short, and then there is this is called the Pauli dimagnetism, because you see the susceptibility is positive. Then there is the Landau paramagnetism. The susceptibility will be negative. So I will be happy if we can also finish that one. So we can give a break. You see, the basic idea is just, we already have the basics, just apply the basics to various systems.